So we've just shown that the acceleration for an object following constant circular motion is equal to v squared on r. Now, Newton's second law tells us that in order to accelerate, we need to have an unbalanced force, and that unbalanced force divided by the mass is equal to the acceleration. Or in other words, F is equal to ma. So to work out the centripetal force acting on an object, all we need to do is multiply the centripetal acceleration by the mass. So the formula for the centripetal force felt by an object is the force is equal to mv squared on r. Let's have a look at a demonstration now which will make use of this relationship. Now, what I have here is a device known as a whirligig. What it is we've got a small tube here and a ball on the end of a string here. What I'm going to do is start the ball turning round, and then I'm going to pull on this string, so that will decrease the radius of the circular path that the ball is tracing out. So I want you to observe the relationship between the radius and how quickly the ball is moving. Let's do that again. In order to clearly see what's going on, we actually need to rearrange the formula a bit. So we've got F is equal to mv squared on r. But it's hard to tell directly how fast it's moving. We could see that the angular speed was increasing. It was taking less and less time to travel a circle, but it was very hard to see how quickly the ball was actually moving. So into here, let's substitute v is equal to omega r. So we've got F is equal to m omega r squared on r. And so this is equal to m omega squared on r, which is equal to m omega squared r. Now what was happening as the radius was decreasing, omega was increasing. It was covering the angle more and more quickly. And that's because I was applying a fairly constant force on it. So as the radius decreased, the angular speed needed to increase. What I have here is a bucket of water. If I can spin it fast enough, then there should be enough force to keep the water in the bucket even when the bucket's upside down. So let's have a go. Okay, and just to show that there is water in the bucket. So let's solve a problem. So the question is, a car travels at a speed of 45 kilometers per hour around a curve with a radius of 50.0 meters. What minimum coefficient of static friction is needed to keep the car on the road? Okay, so let's start by drawing a diagram. We've got a circular path like this. It's got a radius of 50 meters. And so in order to accelerate around here, the car needs a force towards the center of the circle. And that force will be given by mv squared on r. This is the force that it needs to account for its change in direction. And the thing which is going to apply this force is the friction. So we're going to have the amount of friction is given by the coefficient of static friction times the normal reaction force, which is equal to mu s times mg. And so what we have is mv squared on r is equal to mu s mg. These m's will cancel out. So now we know what r is. We know g, it's the acceleration due to gravity, which is 9.8. And so we need to work out what v squared is. So v is equal to 45 kilometers per hour. So that's equal to 45 times 1,000 meters over 60 times 60 seconds. So that is equal to 12.5 meters per second. And so we have what we're trying to work out is mu s. So we can rearrange this. We've got mu s is equal to v squared on rg, and so this is equal to 12.5 squared over 50 times 9.8, and solving that on the calculator we get 0.32. So that's the coefficient of static friction that we need.